Hey everybody, this is John Buck. I'm back with another array signal processing video. In this video we're going to talk about some issues with practical adaptive beamforming, and specifically the case where we don't know the true spatial covariance matrix. So we need to estimate that from observed data. And when we do that, we never really have as much data as we want in real life. Particularly the larger the array is, the harder it is to do that. We may have a sample covariance matrix that's actually singular, that is not invertible. And even if it is invertible, it may not be that accurate. We saw a little bit of that last time. So people have come up with lots of engineering strategies to deal with that. And today we're going to talk about a couple of them, particularly in today's class. We'll talk about the dominant mode rejection beamformer and the Eigenspace projection approaches, which are sort of a family of approaches that are all fairly in the same general neighborhood. So I'm going to start in this first video just sort of reminding you what some of the issues are and laying out the challenges. And then there'll be a following video where I'll describe the DMR beamformer algorithm. And then when we get to class, we'll talk some more about how it performs, show you an example of that, and also talk then about the Eigenspace approach. All right, so let me pause the video here and we'll switch over to the whiteboard. Again, our topic for tonight is practical adaptive beamforming, and this is the case where we don't know the sample covariance matrix S, which is, in theory, is defined as the expected value of XX Hermitian, but we would need to know the PDF of X, of our observed data X, to get this expected value exactly. And in the real world, we don't know that. We just have some array out there measuring data, and if we knew what everything was and where it was that we could write this down, well, we wouldn't need to be beamforming, would we? So what we often do in practice is we get some collection of data, some K measurements, and the key idea is that during that time that we take those K snapshots or K measurements, we assume the world is not changing very much, so it's safe to average these, and so we can get some estimate of S hat, right? And this is basically relying on the law of large numbers, right? The law of large numbers says that averages, loosely speaking, an average converges to an expected value as I get more and more data under some regularity conditions. And so when we do this, we end up finding the sample covariance matrix, and our goal ultimately, what we'd like to do, right, our sort of aspiration or our dream, is that we want to go use MBDR, because we know if we know the sample covariance matrix, that's optimal. We can say this is sum alpha times S inverse times V naught. And we've seen in class that this can also be interpreted as the whitening filter with a match filter, right? That we whiten our background, whether it's spatially colored diffuse noise or some discrete interferers, that we can whiten that out. And so that's our goal. And in practice, we often have to replace S by this alpha hat, or S hat rather, where this gets applied. And so we end up with some estimate of what, this would be Capon's true MVDR. And we often call this SMI for sample matrix inversion. Now, the problem we saw in class is that if K is, well, we can have a couple problems, right? The first problem, let's not get too far ahead of ourselves, is that if K is less than the number of sensors, right, that means the amount of time I can average coherently, combining things without the world changing too much, is less than the number of sensors in the array, which can happen when things are changing quickly, or when I have a very large array, this will happen. This makes a problem because S hat is singular, right? Which means I cannot take the inverse. Actually, that's so important, maybe we'll write that in red. Right, so if the number of snapshots, right, is less than the number of sensors in my array, this estimated spatial covariance matrix, S hat, will be singular and its inverse will not exist, right? So it's not an invertible matrix, so I can't do all this. So I need to find a way to solve that problem. The other problem we saw when we looked at the SMI material in class is even if k is bigger than n, like we saw, we had the example we looked at where k was twice the number of sensors, some eigenvalues of S hat will be close to 0. So when I invert them, so 1 over the lambda gets very large, and the net result of that is that the norm of my weight vector grows large. Right? I end up having a very large norm squared of my weight vector, which means my white noise gain is going down. And we also saw that my sensitivity to perturbations in the elements, right? The location to element perturbations, either in their location, either in their location or also just in the phase and gain of them gets more sensitive as W squared grows large too. So there are a lot of reasons I want to keep this small, and this is not helping. Unless I have a lot of snapshots, maybe more like 10n, I'm going to have problems with this. And there's a whole field, beautiful field of mathematics called infinite random matrix theory that has some very powerful results about how will the sample covariance matrix eigenvalues be related to the true ones. Now we're not going to get into that here. We might spend one class on it late in the semester. But let's talk more immediately about that's fairly recent research, very active research in array processing on how we can use infinite random matrix theory to analyze practical beamforming algorithms based on the sample covariance matrix. But instead for today, I'm just going to mention a few of the strategies, one we've seen already, and then sort of previewing the other two we'll talk about in this class. Okay, so a couple strategies for snapshot limited adaptive beamforming. One we saw last class, if you try to challenge your memory a little bit, pause and remember, what did we see what could we do to the sample covariance matrix to improve the performance? Right. So hopefully coming back, if you've remembered, the first one we saw is often called diagonal loading. And this often comes about just sort of ad hoc or good intuition, saying, well, if I add diagonal loading, I'll keep W squared in control. But we saw this actually came directly if I do the Lagrange solution to keep an upper bound on the weight squared. If I say I want this to be less than, say, some T naught, that says I'll put an upper bound on how large the weight vector norm squared can be. That's equivalently putting a lower bound on the white noise gain I'll accept. And the problem with this, pause again and see if you can remember the problem before I tell you. It's always good building stronger memories by challenging yourself to remember. All right, one problem is we cannot directly find the diagonal loading, right? Find the gamma for diagonal loading, or when I go to S hat plus gamma I. We cannot find this directly as a function of T naught. Like there's no closed form function where I say that gamma is I go take T naught, plug it into some function, and it tells me what gamma is. I can only find it with iterative solutions. Doesn't mean it's still not a good idea, but it does mean that you sort of have to do some trial and error here or find other ways to limit the weight vector. And the other approach is to step back for a minute and say, well, if I only get k snapshots, I know I have a limited amount of information available to me. What could I do to limit the number of things I'm trying to estimate from that information? It's not, loosely speaking, I have a certain amount of information. I need to spread it among all the things I'm going to estimate. The thinner I spread that information, the worse the quality of my estimates will be. And so finding what are, the second and third algorithms both sort of fall into the category that I'm going to mention are strategies, maybe even more than algorithms, have a common feature that they're both about reduced degrees of freedom. So both of these find ways to say I'm going to reduce the number of, since I have a limited amount of data, I'm going to find a way to structure the beamformer to reduce the amount of information I need to pull out of those K snapshots. So the first one is very helpful, is known as the dominant mode rejection beamformer. And that's the main thing we'll talk about in class tonight. This was first proposed by Doug Abraham and Norm Owsley in 1980. They were working at the Naval Undersea, Naval Undersea Systems Center, now known as the Naval Undersea Warfare Center. And so I'll say more about that in the next video. But the key idea here, I guess the one other thing I'll say is that this reduces the degrees of freedom by this imposes a structure on the spatial covariance matrix, that it assumes you've got some interferers plus white noise. So it forces the background noise to be white. And so rather than trying to estimate lots of eigenvalues, it turns out it takes all the weak eigenvalues and averages them to use that, and then replaces all the measured eigenvalues with their average for the weak ones. I'll be very precise about that in the next video, so I'm not going to say more now. The other one we'll talk about in class are sometimes known as Eigenspace projection methods. Or sometimes these are called subspace methods. And they're also similarly related ideas are sometimes called beam space methods. And the key idea here is that you actually work in a lower dimensional space, right? In general, the array weights would be in an n-dimensional space. And here we say, well, I'm going to instead find some d-dimensional, lower dimensional space to work in. I'm going to assume I can estimate, or I know a priori, some subspace that contains all the signals and all the interferers, or particularly the signal, that the signal will be within this subspace, and then I'm going to project all my data into this subspace. And so in doing that, I may be removing some of the noise and interferes, and that can only help me. And this can also work really well as long as you're right. But if you're wrong about the subspace, it's like you're sweeping data off the table that you might need later. So it is always a little risky to do that. So I'm going to stop this video here, and then in the next video I'm going to describe the dominant mode rejection beamformer, how it imposes that structure on S before then going on to use the MBDR weight calculations. Okay, well, I will stop here and see you in the next video.